In this video, I'm going to talk about electric flux phi. Let's say we have two charged plates. We have a positively charged plate here, full of positive charges, and we have a negatively charged plate here. This will result in an electric field pointing from the positively charged plate to the negatively charged plate. I'm going to place a rectangular plate in this electric field. Yeah, that's the plate, rectangular plate with an area A. So electric flux is defined as the measure of electric field lines passing through this plate. How do we find electric flux, or what are the factors affecting electric flux? There are three factors. The first one is electric field E. If you increase the electric field, the number of field lines passing through this plate will increase. If you decrease the electric field, the number of field lines will decrease. That means electric field has a direct relationship with the electric flux. So phi is proportional to E, directly proportional to E. Now the second factor is the area of the plate. If you change the size of this plate or the area of this plate, you are essentially changing the number of field lines passing through this surface. If you increase the area of the plate, that will increase the number of field lines passing through it. If you decrease the area of the plate, that will decrease the number of field lines passing through the plate. Yeah. Okay, so again, we have a direct relationship here. So phi is directly proportional to area of the plate, A. And the third factor is the angle or the orientation of the plate. It's called theta. Okay. Let's say the plane of this rectangular plate is parallel to the electric field. So the area vector, how do you draw area vector? Area vector is always perpendicular to the surface. If this is the surface, then area vector will be perpendicular to it. This is the area vector. Area vector is always perpendicular to the surface. If let's say this is the surface, then the area vector will be perpendicular to this. For this surface, this is the area vector. For the other surface, it's pointing to the right. Yeah, so it's always perpendicular to the surface. And theta is the angle between electric field and area vector. So if you have a rectangular plate with its plane parallel to the electric field, aligned parallel to the electric field, then the number of field lines passing through this surface will be 0. Or in other words, if the angle between E and A is 90 degrees, flux is 0. Flux is 0. Now, if the orientation is like this, like in the second picture, then let's say this is the electric field, direction of the electric field. These are the plates. Positive charges here, negative charges here. Electric field is from right to left. Area vector for this surface is towards left. So electric field and area vector are in the same direction. In this case, the number of field lines passing through this surface will be maximum. So the third factor is the angle between electric field and area vector. So we're going to define an equation for phi. So these are the three factors. So phi equals electric field times area times cosine theta. That's our equation. Phi equals EA cosine theta. Or phi equals E dot A. Dot product between electric field and area vector. The integral form of the same equation will be phi equals closed integral E dot dA. That's the integral form. Let's solve some level 1 problems. So we have an electric field pointing to the right, 200 Newton per Coulomb. We have a plate, a rectangular plate in this electric field with length 1 meter and breadth 0.5 meter. So what will be the electric flux? The equation is phi equals EA cos theta. Okay, the angle between electric field and area vector, this is the area vector for this surface. Area vector, angle between them is 0 degrees. So phi equals, electric field is 200. Area, okay, we don't have area, but we can calculate it. Area equals length into breadth. This is a rectangle, so 1 times 0.5, which is 0.5 meters square. Substitute here 0.5 times cosine of the angle between electric field and area vector. They're in the same direction, so there is no angle between the electric field and area vector. So cos 0. Cos 0 is 1, so 200 times 0.5 is 100. What's the unit? It's EA cos theta, right? Phi equals EA cos theta. So unit of phi will be unit of E times unit of A. So electric field is Newton per Coulomb, area is meter square. So Newton meter square per Coulomb. Yeah. The same rectangle, but this time we're finding the electric flux for the opposite surface. So that's the area vector. And what's the angle between area vector and the electric field? Theta equals 180 degrees. Electric field is towards right, area vector is towards left, so the angle between them is 180 degrees. Yeah. So when you calculate phi equals EA cos theta, again same thing, 200 times 0.5 times cos 180. Cos 180 is minus 1, so you'll end up with the same answer with a negative sign, minus 100 Newton meter square per Coulomb. If electric field, I'm going to use orange color for electric field. If electric field and area vector, and blue color for the area vector are in the same direction, then phi will be maximum. Or if the angle is theta, angle theta is 0 degrees, phi will be maximum. If electric field vector and area vector are in the opposite direction, then the angle between them is 180 degrees. Theta equals 180 degrees. So that will give you a negative phi. So that's the negative maximum. Right? What if electric field vector and area vector are perpendicular to each other? So this is the direction of electric field vector, and area vector is perpendicular to it. The angle between them is 90 degrees. 90 degrees. So theta is 90 degrees. Cos 90 is 0. So flux will be minimum or 0. Example 2.5, electric flux through a cube. Figure shows a cube that has faces of area A in a uniform electric field that is perpendicular to the plane of one face of the cube. What is the net electric flux passing through the cube? Okay, so in this problem, we have a three-dimensional object in the electric field. We have a cube. A cube has 6 faces. Total flux phi equals flux through the first phase plus flux through the second phase plus flux through the third phase plus flux through the fourth phase plus flux through the fifth phase and flux through the sixth phase. Yeah. Okay, so this is my phase 1. Phase 1. Phase 1. Electric field vector is in this direction and area vector is perpendicular to the surface. So can't really draw it on a two-dimensional plane, but yeah, that's the direction of the area vector. And what's the angle between electric field and area vector? 90 degrees, right? Electric field is towards right. Area vector is perpendicular to it. So theta equals, this is my phase 1, so theta equals 90 degrees. Theta equals 90 degrees. And what about this phase? Area vector is upwards, always perpendicular to the surface. So it's upwards. So that's the area vector for the second phase. Again, the angle is 90 degrees. Same for the third phase, which is the opposite one, and the fourth phase, which is the phase at the bottom, right? Angle is 90 degrees. So phi 1 equals EA cos 90. Cos 90 is 0, so electric flux through phase number 1 is 0 because the angle between electric flux and area vector is 90 degrees. So 0. Same for phase 2, same for phase 3, and same for phase 4. Okay, so phi 1 is gone, phi 2 is gone, phi 3 is gone, and phi 4 is gone. So we have only fifth phase and sixth phase now. This is my fifth phase, this one. Okay, how do you draw electric flux, area vector for this phase? Area vector is perpendicular to the surface. So that's the area vector. What's the direction of electric field vector? Electric field vector is in this direction. You can see it's pointing to the right. So this is the direction of electric field vector. What's the angle between them? So this is the electric field vector pointing to the right, and this is the area vector pointing to the left. They're in the opposite direction, so angle between them is 180 degrees. So for phase 5, theta is 180 degrees. So for phase 5, electric flux will be equal to E times A times cos 180. Cos 180 is minus 1, so it will be minus EA. Minus EA. That is for phase number 5. Now what will be the equation for phase number 6 then? Phase number 6 is the one opposite to this phase. This phase, you can't really see that, but it's a phase opposite to that one. Yeah, for that phase, electric field is towards right and area vector is also towards right. They're in the same direction. So if you draw area vector, it should be perpendicular to the surface. So it should be in this direction. That's the area vector. That's the area vector. So they're in the same direction, right? So theta equals 0. Theta equals 0. So phi 6 equals EA cos 0, which is equal to EA. Let's call this equation number, equation number 1, this equation number 2, this equation number 3. For a cube, length of the sides are equal for all the faces. So you'll get the same area for all the faces as well. So area is the same. Electric field is also the same. It's placed in a uniform electric field. It says uniform electric field. So electric field is also same. So let's substitute equation number 2 and equation number 3 in equation number 1. We don't have phi 1, phi 2, phi 3 and phi 4. They're all 0 because the angle between electric field and area vector is 0. So we have only phi 5 and phi 6. Okay, so phi equals total electric flux equals minus EA plus EA. They will get cancelled out, so the total electric flux will be equal to 0. Now, what if the question is to find electric flux through only one face of the cube? Let's say this dark face on the left side. So I'm going to modify this question a bit. What is the electric flux? What is the electric flux phi through the dark face? Dark face. Then we have to consider only this face. So the electric field is towards right. Electric field is towards right. Yeah, electric field is towards right. Area vector is towards left. The angle between them is 180 degrees. So phi equals EA cos 180, which is minus EA. Now, if we have values for electric field and area, let's say electric field is 100 Newton per Coulomb and area is let's say 2 meters square, then phi will be equal to minus 100 times 2, which is minus 200 Newton meter square per Coulomb.